Right, just while we're setting up, good morning everybody. I'm just going to put a little circuit up here, and I want you to try and work out what the output is. Okay, you can just have a think about that while we're going through the lecture. Okay, ready to go? Okay, good morning again. So today, for about 45 minutes, 50 minutes, we're going to look at hazards and races, which have to be eliminated from all types of circuits, if you can. And here's a typical circuit. I'm not recommending you design using this, but it could happen that two signals arrive on X, or this could be another X, could be X0 and X1. If two signals arrive at the same time, because this is an AND gate, one input should always be at naught. Okay? So we want the output to stay low. So just have a think about that. And think about propagation delays. See, as we talk about the theory. Have we gone up? Is it coming through? Okay, is it coming? Hello? Hello?
Hello.
Hello, that's the one. Okay, just in case the 7 people that were watching us yesterday on the internet might want to watch us again. I'm glad it's 7 and not 700. Feel far more confident. Okay, so hazards and races. Not only hazards apply to asynchronous circuits, they apply to synchronous circuits as well. So you may have learned about it when you're doing combinational logic or synchronous design. So as engineers, you want to try and eliminate hazards. But in these type of circuits, asynchronous circuits, we're talking about 3 main types: static hazard, dynamic hazard, and essential hazard. And we want to try and eliminate these hazards, which is what we're going to do for this first lecture. So static hazard is caused by uneven delays in a combinational circuit. So like this one I've drawn here, you might want the output to stay logic 1, and you get a spike or a glitch down to logic 0. I call that a static naught hazard. Some textbooks call that a static hazard in the ones, because you're at a logic 1. It means the same thing, an unwanted spike. Now if that was a combinational circuit like this, and you had us coming through, and it's displaying, say, the display on your watch or whatever, you probably couldn't see it. Might be in a few nanoseconds or even sub-nanosecond nowadays. But you want to get rid of it. If that spike is high frequency, that will radiate out. Could give us problems with this EMC we talked about the other day. High frequency spikes could interrupt or interfere with other equipment. And it uses power, even though it's only a short spike. And it might be random. It could actually interfere with other parts of your circuit if you're on a circuit board or inside a chip. And the other one is, if you want the circuit to remain low, you get a spike to 1. So there are 2 hazards. Good news is we can eliminate them if we want to. Dynamic hazard, a bit more tricky, but again we can eliminate it. When you've got different path lengths in the circuit, really if you want an output to go from 0 to 1, like this, nice and clean, if you've got a multi-input gate, 3-input gate, 4-input gate, signals arriving at the input at different times, so instead of having a clean 0 to 1, it's going 0 to 1, but with a couple of ups and downs in between. Now again, if that's a static logic circuit, it might not be a big problem. But again, it's using power, switching up and down when you don't need to. But in this type of circuit, we've seen already, if we want this output to go 0 to 1, it goes, so if that's say that's state 1, so there's state 1, it goes high, let's take us to state 2, and we expect it to stay high. If it goes low again, it's going to take us to an unknown state, unless it's supposed to go low again, which is unlikely because there might be more than one input. So we've got to try and eliminate that. So the bad news is, essential hazards can't be eliminated. They're inherent in the design. Okay, so you have to just use good design practices to try and eliminate them. Difficult to solve due to the logic structure of a circuit. And if you look in a, I don't know if you still look in TTL data, look in a data book of say a D-type flip-flop or latch, you'll have a setup and hold time. Do you know what setup and hold times are? It means you have to set up the data and hold it as you apply the clock. Because inside that D-type latch is an asynchronous circuit. If you set them up at the same time, or you bridge or you break those rules, it probably won't work. So you get around it because in this type of circuit, essential hazards, I'm not going into any detail, are basically due to when a signal arrives at a secondary state gate, before the primary signal arrives, maybe due to a signal traveling a long way around the circuit. And the secondary signal will influence the circuit, one of the Y signal outputs, before the actual primary signal X gets there. So you can do this by routing the signals to try and minimize that problem. Some textbooks say put delays in. I advise against putting any delays in, just reroute the signals. So if one signal's taken a long time, make sure you can route it a different way. Right, we're just going to do a quick exercise on the board, just to see what a static hazard is, but before I start that, has anyone solved this problem? Will we get that? If I put a pulse into this circuit, do we get a nice clean output? No? Well done. What do we get? A spike, that's it, we're going to get a spike because we expect, when we're going 0 to 1, problem is, this is not X here. So when X changes, there's a propagation delay. Doesn't matter if it's a millisecond, nanosecond, femtosecond. So not X, which is the opposite of X, will change, but there's some delay there. Okay, so this bit here is TPD of that inverter. Okay, propagation delay of the inverter. So because that's moved that way, I've got the blue pen. In this area here, both of the inputs are 1, which means the output is 1. So at that point there, we're going to get the spike. Bad news. But it's an artificial circuit. You wouldn't really make a circuit like that where you're going to put the same signal inverter into an AND gate, normally. But if you want to test, if you've got time in the lab while you're here, there's a nice circuit to test how fast can your gate switch. Because all you're doing here is finding out what the delay of that inverter is as it moves through. If you can measure that spike, it'll give you some clue about how fast you can switch the circuit. So for testing, it's quite good, testing a small circuit. And you can extend this, obviously, to other circuits. And if you wanted a series of spikes, you just put a clock in there. This is just a single cycle. You put a clock in there, another one there, you get another spike. If you want to put spikes into a circuit, this is a very good way to generate them in hardware, or in simulator. So we're going to consider a static hazard. Have you all got this down? Can I take that off for now? Well, I'll just leave that part for now. So we're not going to do a full design because we're short of time, but when we get to the sort of things we get. for example. If we're part way through a design, we've got a secondary Y map like this. These are the groupings we can do. Okay, so when we do these groupings, I'll put the equation down and we'll draw the circuit quickly. Y, X naught, or X naught, X1. So I'll draw the circuit underneath. Right, so you should all follow the circuit by now. So gate 1 is Y not X naught, that's this one. And gate 2 is X naught, X1, that's this one. What I'm going to do is move the inputs from 1, 1, the initial conditions, to 0, 1. Okay, so for the sake of example, we're going to see how the signals propagate through the circuit. So we're starting with initial conditions. So the inputs are 1, 1. So if I draw it in this case, that means you've got a 1 and a 1 going in there. If you draw it, leave a space because I'm going to put 2 or 3 signals after this as the time marches on. So 1 and 1 into there, give us a 1 out of there. 1 into the OR gate gives us a 1. This will be naught. Android is naught here. So that's stable, and if you look at the circuit, we're in that square in the circuit. Inputs are 1, 1, and the Y output is 1, so the Y input is 1. So quite simple, we're just going to move effectively. We're going to turn gate, so this, sorry, let's do this. This is a naught, so that's a naught. So what we're expecting to happen is, as we move from one group to the other group, this output Y should stay at 1. And again, due to this pesky inverter, puts enough delay in there to cause us problems. So effectively, when we do this next, we're going from 1, 1 to 0, once we're going from 1, 1 to 0, once we're going from this square to here. So we jump in effectively from this square to here. If the circuit's working correctly, the output shouldn't change. So let's see what happens in reality. So now in blue, we've gone to 0, 1. So what I'm going to do is draw the time steps, and if nothing happens, I'm putting a dash in. We're going to now start building in the propagation delay of the circuit. For exercise, we'll just assume a dash means that there is a delay. Obviously, inverters will be the quickest, and these 2 input gates will be slower. Similar order of magnitude, but there is a difference. So That's 0, 1 now going to here, so that's a 0. That's not changing. So 0, 1 into there will give us a 0, but I'm going to assume with the propagation delay I'm going to indicate by a dash. So sometime later that'll go to a 0. For example, 10 nanoseconds. The same on the inverter. That's going to go from a 0 to a 1, but with a delay. So sometime later that'll go to a 1. At the moment nothing's happening there because we've still got a 0 going in, so the output there is still 0. And nothing's happening there because that 1 is still seen there. So a problem occurs when we step it on another step in time. Because this one, this 0 is acting straight into this gate directly on the change, but this 1 acting into this gate is delayed by this inverter. So what it means is this output will change first, which it does, and this output will be delayed another 1 and eventually goes to 1, but by that time it's too late. If you're unlucky, after another dash gap, this will go to 0 due to the delay of this one, and after that we don't know what's going to happen. Okay, Joe, follow that? So we're stepping along in time. So ideally we want these two circuits to switch together, or the new circuit was going to want to switch before the other one. The problem is this signal's delayed by the inverter, so this one switches to 1 after this one's already turned off. So there's a gap. So how do we do it? Well, we have to bridge that gap. And we saw how to do that the other day. We need to put a new gate in, which is linking the two groups, this one, which is YX1. And we should be able to see now that all the time Y is to 1 and X1 isn't changing. X1's at a 1 all the time. So you put that new gate in and that solves the problem. So that's how you cure static hazards. Very easy. Okay? 5 minutes. Now do you want the other news, good news, 10 seconds. If you cure static hazards, dynamic hazards at the same time. You don't get free lunch, well you do here, but don't often get something for nothing. So you get dynamic hazards as well by linking them all together. I think that's pretty good. Essential hazards, we're not going into anything because it's too difficult to solve in 5 minutes. Okay, so just a couple of notes on that. And then we'll go into a quick race. So there's new linking gate. Let's write it over here. So we've added this new linking gate, which effectively is building a bridge between the two groups. So to remove static hazards, link all the groups in the secondary maps and add additional gates to maintain required output for output transitions. And what I said earlier, good news. Okay, so a bit long-winded, but if you eliminate all static hazards, you can forget about dynamic hazards because you've also eliminated them as well. Because by linking the groups, you've taken account for any of those delays in actually gate delays or signal path. Okay, so any questions? You're all happy? We're flying, so now I've got a race design towards tea break. I'll just leave that while you copy it for 1 second. I'll sort out some notes. Have you all got this top bit down? Yep. Because we've gone through it quickly, I've got enough time to show you the waveforms which will reinforce what's going on here. So what I'm going to do quickly is draw out what happens inside the circuit if you look at the waveforms. So we're just going to do a quick waveform diagram. X0, X1, we need not X0. We need gate 1 output, gate 2. Gate 3. Right, so that's our starting point, which I'm going to relate to that circuit quickly. X1 isn't changing and just stays high. X0 is going from 0 to 1. So not X0 is going through our inverter. So the first thing I'm going to show is the delay on that inverter. So we'll just dot that down so we can see where we're starting from. So TPD usually means propagation delay, INV means inverter. So when this X0 changes, sometime later, the inverter will change. Okay. So then when does gate 1 change? Well, gate 1 will change after the inverter's changed. I'll draw it slightly bigger because bigger gate, TPD and. So at that point, this gate 1 should go high. Like that. Okay. So we'll assume that gate 1 and 2, both AND gates got similar delay. In reality, most gates will be quicker switching high or low, but it's marginal. So it's about the same for this exercise. So gate 2 is going to go from high to low. So it starts high, it goes low after that delay, continues on. So at this point, gate 3, these are the two inputs to gate 3. Gate 1 is a naught, and gate 2 is a naught. So gate 3 sees two naughts, which means the output will go to naught. But again, there'll be a delay. Once it goes to naught, we've got the wrong answer. We didn't want the output to change at all. So these two naughts, after a propagation delay of the OR gate, will force the output to naught before the next input starts to act on it. In other words, this input going high through that inverter. So all we need to do really is add up all the delays. And even though an inverter delay will be less than an AND gate, it could be half. Because you've got that delay in there, it's put the sequences, but with the two inputs here, 0, 0, if they just switched at the same time, the two gates 1 and gate 2 would have crossed over. So when we put the new gate in, the linking gate, it's got an output of 1 all the time in this transition. So even though those go to 0, 0, the linking gate is going to keep it high. Okay? Yes, sir? Yeah?
If you consider that static hazard is 0 and dynamic hazard is 1, then what would be happen?
Static hazard and dynamic hazard is not the same thing. Huh? Static hazard and dynamic hazard is not the same thing. Static hazard due to the gate delay, dynamic hazard due to the path lengths. So I'm not sure what you're asking. You can talk to me later. You'll need to finish in time. So we need to move on to the races because we're racing to T. So a race in this context can occur when two signals change together. For example, if we're going from 0, 0 to 1, 1. I think I did mention it earlier, but we don't know if you have that situation go from 0 to 1, 0, 0, which signal will change first. And for this type of circuit which have memory and feedback, you could go 0, 0, 1, 0, 0, 0, or 0, 0, 0, 1. It'll take you to the wrong state. So be avoided because it'll take the secondary out of step. And what we're going to do in this example, which is the real example I did mention from one of our research projects, you can add in a cycle to eliminate the race. Okay, so now we're going to try that. So this is a design which was used to detect particles passing through a laser beam. Just so you know the context, particles passing through a laser beam, and the laser comes on one, it's detecting when the particles are really there or they're not. So it's very fast. Particles are passing in a flow, could be an airflow or a water flow, and you're counting hundreds of them. So it's a fast circuit. So it's actually got two inputs. So we've got 4 columns. It's actually got 6 states in this design. We've got 6 rows in the table. We've been given these tables partway through the design, and we've got to make a working circuit. Okay, so that's the table we're given. So I'm going to very quickly run through the implication table to see which of those states can be combined. So we're going from state 1 to state 2, state 2 to state 3. State 2 can go back to state 1, 3 can go to 4, 4 go to 5, 5 to 6, 6 can go back to 3, or 6 can go back to 1. So as yesterday, we draw up the implication table. So it's quite a big one. Okay, so I just want to run through this quickly because the main point of today is to find the races. So when we look at the combinations, state 1 and 2, you should be getting the hang of it now. There's no problem, we can combine that. States 1 and 3 is implied on 2 and 4. States 1 and 4 is implied on 1 and 5 and 2 and 4. 1 and 5, two stable states in the same column with different outputs. So that can't be done. So you have to cross that one off. 1 and 6 is implied on 2 and 6. So that's the first column. Second one, states 2 and 3 implied on the combination of states 2 and 4. 2 and 4 can't be done. Two stable states in the same column with different outputs. 2 and 5 implied by 1 and 5 and 2 and 6. And 2 and 6, again, two stable states with different outputs in the same column, so the same inputs can't be done. 3 and 4 can be done. 3 and 5 implied on 4 and 6. 3 and 6 implied on 4 and 6. 4 and 5 implied on 4 and 6. 4 and 6, 1 and 5. So we're nearly there. Last one, 5 and 6 implied on 1 and 5. So unfortunately, 1 and 5 can't be done, so you have to cross over ones which are implied on 1 and 5 off the list. 2 and 4 can't be done, which kills most of the others. 4 and 6 can't be done, so that eliminates those. And 2 and 6 can't be done, so that eliminates that. So we can only make two combinations. They're not bad, 2 down to 4. So therefore, combine states 1 and 2 into a new state 1. We're going to combine states 3 and 4 into a new state 3. So we need to revise the state tables, which I'll try and squeeze in here. So input state table, output state table as usual. Okay, so what we did when we combining things, combining 1 and 2, so we're squeezing the top 2 rows together. Anything that was a 1 or 2, we're relabeling as a 1. So that just becomes 1, 1, and the 3 stays a 3. And the output will be 0, 0 and a transition state. Okay, so when we're combining 3 and 4, we're going to have 2 states 3, because 4 becomes 3. We've still got transition to state 5 there. So that becomes 1, 1, 1. State 5 stays where it was. That's got transition to 6. That's 1, 1. 6 stays where it was. Got transition to 3 and back to 1. The key point, this trajectory. So far we don't know how many changes we've got between the states. Okay, if it's a binary number, we can design the thing. If it's not a binary number, we're in trouble. So I'll just try and continue underneath. Trajectory. So remember before we showed the states, so 1, 3 now, 5 and 6. So we look at the table. In state 1, we only go to state 3. In state 3, we only go to state 5. In state 5, we only go to state 6. State 6 can go back to 1, or it can go to 3. So now we've got a problem. In the previous examples, we had 4 states and 4 transitions, so we can quite nicely, if you want to put some secondaries on, y1, y0 is 0, 0, then you can go to 0, 1, then 1, 1, then 1, 0, and back to 0, 0. But now you've got this 5th transition, you can't do it without two of the secondaries going from 1, 0 to 0, 1. So how do we solve it? Difficult. Bit of experience required. Let me write it over here. So that's the assignment you'd normally do going around the outside, but how do we deal with this difficult one here? So we'll just do what we do.